I will begin. Hi everyone, I'm David Desobry, currently in thesis in the Pixel team at INRIA Nancy. My thesis is in collaboration with Total, so one of my thesis supervisors is Jeanne Pellerin. Today, Yoann Coudert-Osmont and me are going to present a work in progress on non-orthogonal frame fields generation that we did in collaboration with Etienne Cormand and my two last thesis supervisors, Nicolas Ray and Dmitry Sokolov. I will do the 2D part of this presentation and Yoann will do the 3D part.
Yeah. Hello, I'm Yoann also. I'm currently in last year and fourth year at the ENS of Lyon. This year consists in doing 2 long internships. So I'm currently at the INRIA of Nancy with Sylvain Lefebvre, working on 3D printing. And I will let now David present the 2D part.
So in 2D, for quad mesh generation, we usually use orthogonal frame fields. But orthogonal frame fields on small angles makes degenerated meshes. And so in this case, we would like a simple distorted grid, like here. And to obtain that, we need non-orthogonal frame fields. The non-orthogonal frame fields doesn't have the same topology as orthogonal frame fields. The position of the singularities are different. And in this case, we have 2 singularities for the orthogonal case and no singularities for the non-orthogonal frame field. So in this presentation, I will first talk about orthogonal fields generation to then present the extension for non-orthogonal fields. I will then show some 2D results and Yoann will explain the 3D case. So we represent an orthogonal frame rotated by theta with a function. This function takes a point xy projected orthogonally on the frame to obtain local coordinate x theta, y theta, and then do the L4 norm of this projected point. And in fact, what we have is a 4th order tensor. Now we represented each frame with a function, so each rotation possible with a function. So now to measure the distortion between 2 frames, so one oriented by theta 1, one oriented by theta 2, we do the L2 distance of their representative functions over the unit circle. And after some computations, we get these expressions. And so after a simple change of variables, we can optimize it easily with a least square method. So for the optimization, we first fix the frames that are such that they are aligned with the border. And then we minimize the distortion between adjacent frames inside the domain. So I showed the reasoning to obtain an optimization of orthogonal 2D frame fields. I will do a similar reasoning to obtain an optimization of non-orthogonal frame fields. So this time we represent our frame oriented by 2 angles, theta 1 and theta 2, the same way we did in the orthogonal case. So by the function that takes a point xy projected on the frame to obtain local coordinates and do the L4 norm of these local coordinates. And now, as in orthogonal case, to measure the distortion between 2 frames, this time one oriented by theta 1, theta 2, the other by phi 1, phi 2, we do the L2 distance of their representative functions over the unit circle. And after some computations, we get these expressions. So here we need 4 variables instead of 2 in the orthogonal case. We need the 2 variables for the cos 2, 2 variables for the sin 2, and then we can express the cos 4 and sin 4 with combinations of cos 2 and sin 2. So when we do this change of variable to express the distortion between two frames, we now have an energy that can be solved with a linear least square solver because there is a square expression here. So we use a Casimir-Newton solver here, LBFGS. So for the optimization, this time we fix a single vector such that it is aligned with the border. And then we minimize the distortion between adjacent frame in all the 2D domain. And this time that has absolutely no distortion between each adjacent frame. So with the energies that we just defined, we can generate smoothed non-orthogonal frame fields. I will now show some result of quad meshes obtained from these fields. So with these first results, I want to highlight the fact that removing the orthogonality constraints gives a new degree of freedom for the optimization. And so it gives an alternative to singularities. But it's only an alternative. The solver will just select the solutions that minimize the distortion in the field. And for example, in the domain here, the solver places a singularity in the top right. And in the bottom right, it prefers a high non-orthogonality to satisfy all local border alignment without placing a singularity. Lastly, we can adjust the coefficients in front of the 4 parts of our energy to, for example, penalize less the non-orthogonality, and in this case, favor meshes without any singularity, like in the screenshot A. And vice versa, we can penalize more the non-orthogonality and therefore favor meshes with a lot of singularities inside the domain. But as we can see in screenshot D, if we penalize non-orthogonality too much, we obtain the same degeneratives problem as for the orthogonal case. So this was a presentation of non-orthogonal frame fields in 2D. I will now let Yoann present the 3D extension.
I can't pass the slides.
Oh, sorry.
Oh, I will make you presenter. It's my bad.
Okay. Thank you.
No.
Thank you. It's okay.
Okay.
So I will extend in 2D what that David presented in 2D. So first of all, in 2D we could represent the true bivector as a frame by true angles. I said bivector because they were defined up to the sign. But in 3D it is simpler to directly consider unit vectors with Euclidean coordinates x, y, z instead of using true angles. So now instead of having two vectors given by their angles θ1 and θ2, we will have three vectors v1, v2, and v3 represented with Euclidean coordinates. As before, we can consider a functional f to represent our frame. So this functional is still given by the sum of the orthogonal projection over each axis of the frame to the 4. That is to say, the dot product with each unit vector of the frame to the 4. So if you remember, in 2D, here we add θ1, x θ1, and here x θ2, and we added a third term. In reality, x θ1 was the dot product of u with the vector rotated by the angle θ1. Then I can show you a representation of one term of this functional. So here the vector is very thin, but you can see a blue vector here. It represents the vector v1. And then we deform a sphere a sphere so that we set the radius of each point u of the sphere to the value u.v1 to the 4. And the color depends also on this value. Then the directions where the color is red and where the radius is large are directions where the functional have a high value. In the same way, we can represent the whole functional. So this time with 3 vectors. We have one here in green, one in blue, and one in orange. It's just to give you an idea of what it looks like, because the distortion metric will again be defined as the L2 distance over the sphere between the functional representation of frames. So in order to compute easily the distance between 2 frames, we can decompose this dot product to the 4 in the spherical harmonic basis. So we have terms of degree 0, of degree 2, and of degree 4. This is interesting because it is an orthonormal basis. So with this expression, it is easy to get the distortion between 2 frames. So here we have a frame composed of vector v1, v2, v3, and w1, w2, w3. In reality, this expression is not so nice because there are many terms, and contrary to 2D, our terms are not restricted to polynomials of degree 1 and 2. The spherical harmonics of degree 4 are in reality polynomials of degree 4 in Euclidean coordinates of each vectors. So it will make the minimization of the distortion between frames harder, or at least slower. Another interesting thing is that we can remark that the degree 2 term in the previous expression are null if frames are orthogonal. So if we, for example, pick this spherical harmonics of degree 2, the sum of the x value for 3 orthogonal vectors is 1. It's the same for y and z. So we will have -1, -1 plus 2, that is to say 0. So we can play with the factor here, 81, in front of degree 2 terms to control the importance of orthogonality in the results. So I will illustrate that on this bridge. So here we have a large factor in front of degree 2 terms. We can see that frames are orthogonal or almost orthogonal here. Then if we decrease a bit the factor in front of degree 2 terms, we can see some frames that become non-orthogonal in the left of the image. So it puts the singularity on the border. And if we decrease again, we get the same thing at the right of the image. And the two singularities have been put in the border. So we get a result that looks like a polycube. Now I can show some results on very simple models. So here we have a parallelepiped. We obtain exactly what we want because each frame is the same parallelepiped in smaller. That is to say, each normal of the frames are the normal of the big parallelepiped. And in the right image, we can see that we have a smooth transition between orthogonal frames and non-orthogonal frames here. Here is a harder mesh. The frame obtained is clearly not very good everywhere. but it's a good thing because it means that there are still plenty of work to do. If we look at the zoom here at the left, we can see that frames are flattened in this corner here. It's an interesting result because it is a complicated part to mesh, and orthogonal frames from field will always fail at this point. But we can also see that frames in the ring here are not orthogonal. So it's not what we could expect, and it's not clearly why it's bad. And here in this zoom, we can see also non-orthogonal frames here, whereas we could expect to have orthogonal frames that turn along this part of the mesh. So it put singularity here, but it's difficult to say if it's bad news or if it's good. So we have many kinds of results. Some are good, some are bad, and some are very strange. To conclude, I would say that the current optimization with LBFGS is very slow. It took about 5 or 10 minutes for the last mesh. So maybe we could look at MBO decision methods to get a faster optimization. Or maybe, and it's probably a better idea, we can just apply locally non-orthogonal frame fields. For example, in the previous mesh, we could imagine to compute an orthogonal frame field on the whole mesh and recompute locally frame field with non-orthogonal distortion metric to obtain this kind of results. So there are certainly many works to do to correctly mix some orthogonal fields with non-orthogonal fields. And that's all. Thanks for listening.
Thank you very much for your presentation. Are there any question about this talk?
Yeah, I have a question. Thanks a lot. A very, very nice talk. I like specifically the volumetric extension to the non-orthogonal fields that you presented. So do I understand this correctly, that this is kind of in the end like the spherical harmonics approach, where instead of restricting to rotations, you look at arbitrary affine maps, and then in addition you need the all band 2 coefficients? So that's the way I understood it. And then you found out, which is very nice, that the non-orthogonality is happening only in the band 2 coefficients. And what I actually wanted to ask is, so in your implementation, then you probably also need some projection operator from this relaxation on all band 4 and band 2 coefficients to such an affine map distortion. Or so is there anything special compared to the algorithms that only consider rotations? Or is it more or less the same, that you can do a kind of gradient descent projection?
I don't know if you want to answer. I think in both cases we need to force the norm to be 1, because if we don't, it is hard to reproject. So in our LBFGS solver, we had a constraint on the norm, a small energy that penalize norms to be far from 1, because if we don't, it is hard to reproject, as you said. I don't know if it was the question.
Mm-hmm. Yeah, but so this means that otherwise it's more or less a similar projection. So you could also kind of run MBO style algorithm in the same way as other approaches do.
Yoann, you want to answer? I guess the difference between I don't actually sure what is the question, but the difference with orthogonal frame fields is that if you don't force the norm from one frame to its neighbor, it goes from a norm 1, for example, to a norm 0.1, so the results can be exploited. So I'm not sure about the question, but
so let me try to phrase it differently. So like when we work with these spherical harmonics only band 4, this octahedral variety, and you relate it to the spherical harmonics coefficients, then we also kind of drop in the optimization this unit norm constraint. So why is this more problematic here than in the
it is really hard to explain, but if with non-orthogonality, when you just rotate around a circle and you keep an orthogonal things, even with a different norm, there is no problem, but it's so hard to explain. With non-orthogonality, you use the fact that the sum of the dot products are not 1. It is the fact that the sum of the dot products are not 1 makes you differentiate a non-orthogonal frame to an orthogonal frame. It is really hard to explain, but so.
Well, maybe if you need more time to explain, you can redact a better answer on Discord and maybe do some drawings.
Yeah,
more effective.
That's the idea, that by going to the non-orthogonal one, your relaxation becomes essentially more unstable because just more bad things can happen.
Yeah, I will try to explain more in the Discord.
Thank you.
So, are there any more questions about this talk? Maybe I have a very small one. On the 2D case, you showed that when you remove when you put a bigger weight on orthogonality, you lose some features. But what happens if you put a constraint on these features that you have a non-orthogonal frame right here?
I don't have the. Can you make me presenter so that I can change it?
Oh, well, yes. Sorry.
So.
It's a bit. Well, it's on your results. I don't know when you showed that when you remove the weight on orthogonality.
Yeah.
Yes, here, right here. What happens if you put a constraint on the cross, which is just at the problematic part? Did you try?
No, but that's what Yoann said. It could be a good idea to do like you do. I think we didn't try, but it is what we have to do, at least in 3D, because in 3D the results are really less good than in 2D. So we will try it at least in 3D.
Wow, in 3D it must be way more difficult than in 2D, I guess.
Yeah.
Well, thank you for your presentation again.